Let's begin our dynamic characterization of linear systems with the simplest system we can think of, a first order system. The order of a system is just its number of poles, or alternatively, the highest power of the denominator. So, for example, the order of this system here is n, because n is the highest power of the denominator and the system has n poles. Therefore, a first order system has only one pole, which means that its differential equation involves only y prime of t and y of t. Now we want to calculate the step response of this kind of systems. To keep it simple and get off to a good start, we'll consider that there are no zeros in it. So the general expression of such a system is k, which is the gain of the system, over s over p plus 1. As I said, k is the gain because when s is equal to 0, g of s, that is g of 0, is equal to k, and the pole of the system, or of its transfer function, is located somewhere in the complex plane, somewhere in the real axis at minus p. Now, to find the step response of a system, we have to find the Laplace transform of the output, which is g of s times u of s, when u of s is the Laplace transform of a step, that is 1 over s. So here we get k over s over p plus 1 times 1 over s. Now we multiply numerator and denominator by p to make easier the application of the Heaviside method. So this is s plus p times s. Now we separate this into factors, which are r1 over s plus r2 over s plus p. And we already know how to find r1 and r2. r1 is equal to kp over s plus p when s is equal to 0. This is kp over p, that is k. And r2 is equal to kp over s, just s, that's right, when s is equal to minus p. So this is minus k. If you don't understand this, you can always watch again the videos on the partial fraction decomposition. So y of s, now we know that is equal to k times k over s plus minus k over s plus p. So the inverse Laplace transform is k plus, well, minus, in this case, minus k times e to the minus pt. That is k times 1 minus e to the minus pt. This is the time response, or the expression for the time response of a first order system. Let me draw it. This is the time scale. If here we draw some level for k, the response starts in 0 and it approaches exponentially k, although it never reaches it. So this could be y of t, the step response of certain system. Now there are several aspects worth mentioning here, and the first one is the meaning of k, of the gain of a system. If this is the value of the output, or the final value, although it never reaches it. If y of t tends to k when t goes to infinity, and the input has been a unit step, when, well, if the input is double, that is it is a step with amplitude 2, the final value of the system is 2k. So k is giving us this sense of amplification, or maybe decrease, in the output of the system with respect to the input. So it is informing us about the final value of the system after what we call the transient response. The second comment has to do with the position of the pole, and I want to say that only because P is located here in the left half plane does this response approach some value, in this case k. Had P, or had minus P been this side, we would have got some response like this, never approaching anything. We couldn't even talk about k or gain or anything like that. This is closely related to concepts of stability, and we'll go very deep into that in future videos. Finally, as you see here, the response is not smooth at all. It has some, let me see if I'm capable of drawing it. It has some slope at t equal to 0, and actually we can calculate it. It is very simple. We just have to make dy dt when t is equal to 0. This is equal to minus p, that's plus p e to the minus pt. When t is equal to 0, this is p. So the slope of this line here, of this tangent to the output at 0 is p. Well, this tangent is giving us a sense of how fast the system is, and as you see, the higher the value of p is, so if p goes up, then this tangent is steeper, and the response is faster. It would be something like this, never reaching k. But let me erase that. Another way of characterizing that is by finding this intersection here and drawing a vertical line. Well, we can find that this value here is called the time constant of the system, and actually this value is just 1 over p. So it's the inverse of the pole, and we can also find that at that time the output of the system is 63.2% of its final value. So this time constant is giving us a sense of quickness or rapidity of the system in getting its final value. And in fact, in many books you find first order systems in this form, k over tau s plus 1. I prefer to keep the 1 over p standard, but well, it is up to you. But what I want you I want to stick in your mind is this idea of, okay, I have one pole here minus p, and maybe this other pole here minus p2. Well, the response of minus p, let's say its response is this one. This one corresponds to this pole. Well, the response of a first order system with a pole in minus p2 has to be faster. It has to be faster because its pole is farther away here, which means that its time constant is higher. So we are now relating the time scale with the complex plane, and these are only two of the three ways we will usually take into consideration, being the third one the frequency response, but that will come soon. Finally, a nice property of first order systems is that we can easily find exact formulas for the step parameters of the system. And although I'm not a huge fan of formulas and tables, but, so in this case, in this case, in which it is so simple to deduct them, well, I prefer just to do it whenever I use them. Well, of course, this system cannot have some rise time from 0 to 100% because it never reaches 100%. But we can calculate TR from 10%, for example, to 90%. We can calculate this. We cannot talk about peak time and peak because there's no peak at all. No, there's no such thing for first order systems. But we can talk about the settling time at 5%, or maybe settling time at 2%, or even settling time at 1%. And I'm going to show you how to calculate this one, and you can do it for all the rest. If we know that y of t is equal to k times 1 minus e to the minus pt, and we want to know when the output is 99% of its final value, that is 0.99k, well, we make this equal to 0.99k. And now this k cancels out with this k, and we get here that e minus e to the minus pt is equal to minus 0.01. So plus here, and this implies that minus pt is equal to the logarithm of 0.01, which means that ts, this is ts is equal to the logarithm of 0.01 over minus p, and if we calculate this we get 4.6052, which is almost equal to 4.6. So here we have, sorry, it has to depend on p, so it's 4.6 over p. This is a formula telling us the settling time of a first order system when we consider settling time at 1%. And as I said, we can do the same with all these calculations.